And a very good afternoon, everyone. Today, welcome to today's See.Think Webcast series number 5. So, before we get started, I would like to go over a few items so that you know on how to participate in today's event. So, See.Think Webcast is brought to you by UMP STEM Lab in collaboration with the Ministry of Education, Pusat STEM Negara, Bahagian Kolaborasi Industri dan Masyarakat Ikon Universiti Malaysia Pahang, and Pusat Islam dan Pembangunan Insan Pimpin UMP. So on the left hand side is a QR code and a link to the attendance registration. So every participants will get an e-certificate upon completion of this program. So please register before end of the session today. Our webcast today is at live via UMP STEM Lab YouTube channel as well as via Icon UMP Facebook page. So please be patient if you experience any technical or any internet glitches during the webinar. Now, if the session is disconnected abruptly at any point of time, please hang on tight as the show will go on and we will definitely be right back in a short while. So you will have the opportunity to ask questions to today's presenter by typing in your questions in the comment section via YouTube or Facebook comment. You may send in your question at any time during the session, during the presentation. We will collect these questions and address them during the Q&A session at the end of the presentation. If you would like to contact us, please email us via umpstemlab@ump.edu.my. So before we begin today, I would like to introduce you to UMP STEM Lab. Established back in 2016, UMP STEM Lab is a consolidated effort by staff and students of University Malaysia Pahang to engage with the community with the aim to nurture the interest in STEM. So via the philosophy of see, think, explore and marvel. Now, we strongly believe that early exposure will ignite interest among youngsters to take up STEM in their future. Now, with this engagement, UMP staff and students become mentors and role models to young school children. And apart from upskilling classes, there are also interaction between teachers and lecturers, as well as it is a platform to discuss and to share on the best practices in STEM teaching and learning. So over the years, we have collaborated with various industry partners, locally and internationally, as well as with agencies from government and non-government organizations. So cumulatively, we have engaged with more than 8,000, almost 9,000 school children and teachers in our outreach program. So today, we would like to bring this See.Think Webcast series number 5. Now, the aim of this webcast is to be a platform for discussion on various trending topics that are related to science, technology, engineering, and mathematics, as well as to feature role models and icons to share their exciting journey taking up STEM career pathway. Okay, today we are delighted to have Dr. Adlyka Annuar on board. So before we begin, let me introduce Dr. Adlyka. So Dr. Adlyka completed her secondary education in Sultan Abu Bakar Girls' School in Muar. She later pursued her Bachelor of Physics and Astrophysics degree in 2013 in the University of Sheffield, United Kingdom. And later she pursued her PhD in Physics, Astrophysics in Durham University, United Kingdom in 2018. And now Dr. Adlyka is an Associate Professor in Universiti Kebangsaan Malaysia. So without further ado, I would like to welcome Dr. Adlyka on board. And Dr. Adlyka, how are you doing?
Hi, Dr. Nurul. I'm good. Thank you very much.
Okay, over to you, Dr. Adlyka.
Okay. Thank you, Dr. Nurul. Can you all see my slide?
Yes.
Yes. Okay. So first of all, I would like to thank the organizer for inviting me today to share my knowledge about space science with all of you today. So I've been told that there might be some international participants, so I'll be talking mostly in English, but kita campur-campur lah. Okay. My topic for today's talk is Be Immersed in Space. So this title is quite broad, but I don't have time to cover all of our universe, of course. But I will be covering, I think, the basic of our universe, so that it will provide you with a basic understanding of our universe. So the four topics that I'll be talking about today is, first of all, about our solar system, which I think is important for you to at least have a basic knowledge or general knowledge on this. And I'm sure some of you already know about our solar system from school or from your general reading. And then I'll be talking about stars. What is star? How do you define a star? How do stars evolve? And how would they die in the future, including our sun? And then I'll be talking about a more specific topic, which is on black holes, which I think people expect me to talk about this. So I'll be talking about this as well. And then finally, I'll be talking about galaxies, including what would happen to our galaxy, the Milky Way, in the future. Okay, so let's start with our solar system. So this is an artist's illustration of our solar system. So a solar system is basically a planetary system with a star at the center, and in our case, the star is our sun. Okay, so our sun is at the center of our solar system, and then we have other objects orbiting or circulating around the sun. And these objects include planets, dwarf planets, asteroids, comets, and a lot of other things as well. So in our solar system, we have 8 planets. Okay, we used to have 9 planets, including Pluto, but in 2006, if I'm not mistaken, Pluto was kicked out of the planet category. So why is this the case? So let's see first what is categorized as planet. So there are 3 criteria that a planet should have to be defined as planet. Okay, so according to the International Astronomical Union, a planet must orbit a star. Okay, which Pluto does. Pluto orbit our sun. Okay, the next criteria is that a planet must be big enough to have enough gravity to force it into a spherical shape. So this has something to do with hydrostatic equilibrium for those that are expert in physics. Okay, so it must be big enough so that it can form a spherical shape. So Pluto does satisfy this criteria as well, because it is spherical in shape. But the last criteria, which said that a planet must be big enough that its gravity managed to clear its orbit from any other competitor object or similar size object. So this is the criteria that Pluto does not satisfy, because in Pluto's orbit, there are some other objects. To be specific, there are comets in the vicinity of Pluto's orbit. So this is why Pluto was kicked out of the planet category many years ago. Okay, so back to this picture here. So we have 8 planets, starting from the beginning here. Mercury, the closest to the sun, and then we have Venus, and then of course Earth is the third planet from the sun, and we have Mars, and then afterwards we have Jupiter, which is the largest planet in our solar system, and then we have Saturn with this beautiful ring around it, and then we have Uranus, and the last planet is Neptune. And in between Mars and Jupiter, we have what we call as the asteroid belt, which where most of asteroids reside. So a lot of asteroids reside in the asteroid belt. And then we have at the outer part of our solar system, we have another belt that we call as the Kuiper belt. So this Kuiper belt are mainly made up of comets. Okay, instead for asteroid belt they are asteroids, and for Kuiper belt mostly are comets. Okay, and then besides planet, asteroids, and comets, we also have dwarf planets. So dwarf planets, they are bigger than asteroid and comets to be categorized as those objects, but they are smaller than planet. So they are called as dwarf planets. We have 4 dwarf planets in our solar system. The first one is, of course, Pluto here, located here. And then we have Maki here, and then Aries. And then the last dwarf planet is Ceres, located near the asteroid Belt. So these four are called as the dwarf planets. And then the first four planets, including the asteroid belt, from Mercury and asteroid belt, we call it as the inner solar system because they are located at the inner part of the solar system. And then from Jupiter until the Kuiper belt, or beyond that, beyond Jupiter, we call that as the outer solar system. And the first four planets, we call them as terrestrial planets because they are mainly made up of rocks. And then the last four, sometimes we call them as the giant planets because, as you can see, the size is much, much larger as compared to the terrestrial planets. And Jupiter and Saturn, they are called gas giant because mostly they are made up of gases. And then Uranus and Neptune, they are called ice giants because they are mainly made up of ice. Okay, so that is the basic structure of our solar system. So let me just zoom in a little bit to our asteroid belt here, located between Mars and Jupiter. In contrast with what you might have seen in sci-fi movie, where when you enter the asteroid belt, you must be prepared and be careful. You might be, collide with asteroids, a lot of asteroids, okay? But this is actually not the case, or not true, or not accurate at least, because the size of the asteroid belt is relatively large, but the content is relatively low. The total mass of all the asteroids inside the asteroid belt is about 0.05% of the mass of the Earth. Okay, so the density is actually quite low. So if you were to enter the asteroid belt, you might not even realize that you are in the asteroid belt because likely that you won't see any asteroid at all. Okay, so what you're seeing in the sci-fi movie is not very accurate. So that is just a fun fact about the asteroid belt. So now I want to talk a little bit more about the Kuiper belt. So the Kuiper belt is the outer part of the solar system that is orbiting the sun, okay, where most of the comets reside. Not most, short period comet reside. Okay, beyond the Kuiper belt, we have another structure that we call as the Oort cloud. So this Oort cloud is basically a spherical shaped cloud that surrounds our solar system. Okay, so this cloud is still hypothetical, theoretical, but we believe that it exists because it can explain the origin of long period comets. Okay, so both Kuiper belt and Oort cloud where comets reside. But for Oort cloud, the comets are long period comets, meaning that the period of the comet, the orbital period of the comet, usually is more than 200 years. Okay, and for Kuiper belt, usually for a short period comet, meaning that the orbital period is less than 200 years, meaning that it takes 200 years to at most 200 years to complete its orbit around the sun. Okay, so that is basically about the Kuiper belt and the Oort cloud. So how do our solar system form? So like many other objects in our universe, they usually start with a big cloud of gas and dust that are so dense that they cannot withhold themselves against gravity. So they will start to crush or collapse under gravity, under its own gravity, and then they will form other things like stars and planets. So in this case, our solar system was formed in similar way, in which there is a large cloud of gas that is so dense that it's collapsed, it forces it collapse under gravity, and then at the center of the cloud, where it is the most dense, that will form the star, which is our sun. And then as the cloud collapse, angular momentum will force the cloud to flatten into a disc shape like here. Okay, so at the disc shape is all the materials in the disc will clump together, and those parts will form planets, asteroids, and other stuff in the solar system. So that is basically how our solar system is formed. Now I would like to move on to stars. So what is actually a star? So this is an image of our sun taken in 2012, I think, showing a flaring activity, as you can see in this image just now. So what define a star? So basically, star is just a hot ball of gas. Okay, just a gas, totally gas, mainly hydrogen and helium, and some have more heavy element content. So for our sun, about 70% of the content is hydrogen, and about 20+% is helium, and the remaining is more heavier elements such as carbon, oxygen, nitrogen, and so on. So stars, they are powered by nuclear fusion. So the radiation or the light that you see from the sun is actually as a result of nuclear fusion reaction at the core of the sun. So they are powered by nuclear fusion reaction, mainly converting hydrogen into helium. So this is the basic properties of our sun. So the mass is about 2 times 10 to the power of 30 kilogram, which is equivalent to about 330,000 the mass of our planet Earth. And then the radius is about 700 million meters, which is about 100 times larger than our planet. And then the surface temperature, the temperature at the surface of the sun is about 5,500 Kelvin. But at the core, at the very center of the sun, the temperature is much, much higher than this. The temperature is 15 million Kelvin. So this temperature is what allows it to carry out nuclear fusion, converting hydrogen into helium, and that results in the radiation or the light that we see from the sun. Okay, and then the age of the sun is similar, of course, similar to the age of our solar system, which is about 4.5 giga years or 4.5 billion years. So we think that you might think that our sun is special. You know, oh my God, it's so large, it's so massive. Okay, but sun is actually just an average star in our universe. Okay, there are a lot of other bigger and more massive star in our universe. For example, here I show you one of the largest star that we know, called Betelgeuse. It is a red supergiant star. So this is the image of the star, the orange color object, and this is shown in comparison with the solar system. So as you can see, the size of this star is almost similar to the size of the Saturn orbit. Okay, Saturn orbit. So it's very, very huge. So in comparison with the sun, here is the sun here at the center. So as you can see, or maybe you can't see it because it's very small. Okay, so sun is very, very small as compared to this star here. Okay, so our sun is not that special, but there is something unique about our sun. For example, it is a single star in our solar system. About 50% of stars, usually we found them in a binary or multiple system, meaning that there are usually 2 or more stars orbiting each other. In fact, a lot of outer solar exoplanet system that we found, planetary system outside of the solar system that we found, they have actually more than 1 star in the solar system. Okay, but our solar system just have 1 star. Okay, so that is just one special thing about our sun. So in this video, I just would like to show you how do stars form. So like many other objects, as I said, in our universe, a lot of them is formed starting from a giant cloud of gas which collapse under gravity and then form all these other objects, including our star. So here I want to show you a simulation from a documentary on YouTube that I got of how this process occurs. So let's watch this video first.
All you need to make a star is hydrogen, gravity, and time.
Gravity pulls the dust and gas into a giant, swirling vortex.
Gravity brings matter together. And when you bring matter together and you squeeze things into smaller spaces, they necessarily heat up. It's a simple law of chemistry. You compress something, you drive the temperature up.
Over hundreds of thousands of years, the cloud gets thicker and forms a giant spinning disk bigger than our entire solar system. At its center, gravity crushes the gas into a super dense, super hot ball. Pressure builds until huge jets of gas burst out from the center.
That really shows you how violent a process star formation is. These jets are many light years across. Something is literally accelerating material very fast across unimaginable distances.
Gravity keeps the pressure on, sucking in gas and dust particles that smash into each other, generating more and more heat. Over the next 500,000 years, the young star gets smaller, brighter, and hotter. Temperatures at its core reach 15 million degrees. Only at that mind-boggling temperature can atoms of gas begin to fuse together, releasing massive amounts of energy. And just like that, a star is born.
Okay, so that is just a simulation of how stars form. As you can see, the process is very violent, very high temperature, very high pressure. So this process also takes about 1,000,000 years. So it doesn't occur overnight. It takes about 1,000,000 years for a star to form. Okay, so now I would like to move on to how stars evolve. Okay, once you form a star, how they will evolve and how they will die one day. So this slide here shows you a life cycle of a star starting from birth, from the stellar nebula, which is clouds of gases that form stars, and then how they evolve into their final product, or the stellar remnant that we call. Okay, so stars can be divided into two categories according to their masses. Okay, either average star, which is star like our sun, and then we have also massive star. So massive star is usually defined roughly having mass of more than 10 the mass of our sun, and for average star is less than that. So what would happen once the star has run out of hydrogen at the center, okay, at the core, so it cannot conduct hydrogen fusion anymore. So at that point, it will start to evolve into what we call as the giant stage. Okay, so for average star, it will evolve into a red giant, where it will the radius or the size will expand, and then after that, when it has expanded so much that the outer layer of the star will start to expel from the star itself or from the core. So what you see here is it will become planetary nebula. So in this picture here, you can see at the center the white thing, a white circle thing is the core of the star, and then the blue green color is the outer layer of the star that is being expelled. And then finally, after all of the materials, after all of this green, blue thing has been completely expelled out from the core of the star, or the center of the star, will be revealed as a white dwarf. Okay, so our sun will evolve to become a white dwarf at the end. Okay, so what about massive star? So once the massive star has runs out of hydrogen at their center, so it doesn't have any more fuel, okay, it will start to evolve to become red supergiant. So red supergiant is much, much bigger than red giant. So at some point, it cannot it has grown so large, it cannot withheld itself against gravity, so it will start to collapse and explode in what we call as the supernova explosion. And then depending on the leftover mass after the supernova explosion, the star either become a neutron star or a black hole. Okay, so this depends on the mass left over after the supernova explosion. So if the mass is about 1.4 until 3 solar mass, the mass of our sun, that particular star will form a neutron star. If the mass is more than 3 mass of our sun, it will form a black hole. Okay, so that is how life cycle for a massive star. Okay, so our sun, as I say, it will evolve to become red giant, and then finally it will become white dwarf. So this chart here shows you a life cycle for our sun starting from birth until the end. So we are now about 4.5 billion years. So we are now here, or the sun is now here. So it is approximately halfway through its lifetime. Okay, and then at about 10 billion years, it will run out of hydrogen at the center and start to evolve to become a red giant. And then quickly after that, it will form a planetary nebula, and then finally it will form a white dwarf. Okay, so our sun will not become a black hole because it's not massive enough to become a black hole. So it will form a white dwarf. So this chart here shows you a chart of compact objects in our universe. So compact objects, for example, are white dwarf, neutron star, and also black holes. So the x-axis here is the mass scale for these objects. So white dwarf is the least massive object. So the mass can go up to about 1.4 solar masses. And then we have neutron star. The mass is about 1.4 until 3 solar masses. And then we have black holes with mass of at least 3 times the mass of our sun. Okay, so I will talk a little bit about black hole. As you can see in this chart, there is different types of black holes. So I will talk a little bit about that later. So now I will focus on black holes a little bit. So what are black holes? So black holes are basically an object with so much gravity that nothing can escape its gravitational pull, not even light. Okay, so for example, if you are on Earth, we are on Earth, and you want to go to the outer space, okay, on a rocket. So the minimum velocity that the rocket must have to escape the gravitational pull from the Earth is about 11 kilometers per second. So meaning that you have to travel with a velocity of at least 11 kilometers per second to escape Earth. Okay, but if you are on the sun and you want to get out of the sun, the minimum velocity required is about 600 kilometers per second. So very, very fast. But if you on a black hole and you want to escape the black hole, the velocity that you required is more than 300,000 kilometers per second, which is equivalent to the speed of light, or more than the speed of light. So as we know, nothing in our whole entire universe can travel faster than light. So this means that nothing at all can escape the gravitational pull from a black hole. Okay, so now we know what a black hole is. How do they look like? They look like this. Nothing. You can't see it. It's black. Okay, because whatever light, whatever materials that go into the black hole, it doesn't come out. So you can't see anything. So that is why you call it black hole, because you can't see anything, just black. Okay, but according to Einstein, this is the a basic structure of a black hole. Okay, so the center of the black hole, we have what we call as the singularity point, and then surrounding the singularity point, we have a structure that we call as event horizon. So this event horizon is where the velocity that is required to escape the gravitational pull from the sun is equal to the speed of light. So sometimes we call this event horizon as the point of no return, because once you enter the event horizon, there's no turning back for you, because you can't escape the black hole anymore. Okay. So we cannot see black hole, how do we detect black hole? So one of the ways that we can detect black hole is by detecting the materials that is being eaten by the black hole. So as you can see from this simulation just now, a star was coming too close towards a black hole, and then the black hole starts to accrete or eat the material from the star, and then it emits radiation. So that radiation we can detect using telescope. So that is one of the ways that we can detect black hole. Okay. Another method that we can use is a relatively new method. Okay. We can detect the gravitational wave emitted when two or more black holes collide or merge with each other, and then they will release a gravitational wave. Okay, looks like ripples in the ocean like this. Okay, so that is the gravitational wave. Okay, so these two black holes is about to merge, and at the same time it will release a gravitational wave. So that is what we can detect from Earth. Okay, so the first gravitational wave was discovered in 2016 by the LIGO collaboration. Okay, you might have heard about it. So the first black hole discovered was Cygnus X1, I think in 1960s, if I'm not mistaken. So this is an image of the black hole in X-ray radiation. But as I said, we can't really see the black hole. We can't really detect anything from the black hole. So what you are seeing here, or what we detected, was the radiation coming from the materials that is being eaten by the black hole. Okay, but this black hole was discovered in, or was detected in 1960s, but it was not until many years later that we finally conclude that it is a black hole. Okay. And then in 2019, you might have heard, we finally managed to capture the first ever direct image of a black hole down to its event horizon. Okay, so this is the only image that we have of a black hole. Okay, as you can see, the dark colored circle here is the shadow of the black hole, and then this light here is the material surrounding the black hole or the event horizon. So this is the only picture of a direct of a black hole that we have. Okay, so it was taken in a galaxy called M87. So let's go back to this chart that I showed you earlier. So black holes can be divided into three main categories according to their masses. The smallest one, what we call as the stellar mass black hole. Okay, so its mass is between 3 to 100 the mass of our sun. So stellar mass black hole is what was formed when a massive star died. So when massive star died, it will form stellar mass black hole. Okay, and then the most massive black hole, we have supermassive black hole. Their mass are more than 1,000,000 times the mass of our sun. Okay, and in between stellar mass black hole and supermassive black hole, we believe that there should have another category of black hole that we call as intermediate mass black hole, with masses in between stellar mass black hole and supermassive black hole. So this type of black hole we haven't really discovered yet. Okay, but we believe that they do exist because of the reason that I will talk about later. Okay, but stellar mass black hole and supermassive black hole we have found a lot, but intermediate mass black hole is still debatable or arguable. We have found some candidates, but it's still arguable. Okay, so supermassive black hole, we usually found it at the center of massive galaxies like our own galaxy. And for stellar mass black hole and intermediate mass black hole, we can find them at the outer part of the galaxy, not at the center. Okay. So how do massive black holes form? For stellar mass black holes, it was formed when massive stars die. But how about massive black holes, like supermassive black holes and intermediate mass black hole? Okay, there are several theories, especially for supermassive black hole. The first one is when you have two or more black holes merge together to form larger black holes, like in this simulation you just see just now. Another theory is by accreting or eating materials from other objects such as stars and other things, okay, like this simulation that you have seen before. So they eat the materials and then it can grow up towards more massive black holes. Okay, but for supermassive black hole, there is some issue with this theory, this proposed theory, because the time it takes for a stellar black hole to form a supermassive black hole by accreting material, by eating materials, is longer than the age of our universe. Okay, so that is quite an issue. Okay, so but there are other theories on how supermassive black holes form, such as, you know, the merging of two or more black holes, when or another theory is when it also formed together with our universe during the Big Bang explosion at the beginning. Okay, so now I would like to go back on why we believe intermediate mass black hole exists. Okay, so one of the reasons is because of this theory here. Okay, because in order for the small black hole, the stellar mass black hole, to form supermassive black hole, it must accrete material. Okay, so as it increases in mass, it will reach the mass range for the intermediate mass black hole before it add another mass to form supermassive black hole. Okay, so that is why we believe that intermediate mass black hole should exist, because you know, in order for stellar mass black hole to form supermassive black hole, it must form the intermediate mass black holes first. Okay. Okay, so that is all about black holes. Now I would like to proceed on the last topic, which is on galaxies. So this is an artist illustration, okay, artist illustration of our galaxy called the Milky Way. Okay, so we do not have a picture of our own galaxy. We have a lot of pictures of other galaxies out there, but we do not have a picture of our own galaxy because we are living in it. Okay, so in order to take a picture of our own galaxy like this, we have to travel very, very, very far away to take this picture. Okay, it takes millions of years for you to travel out just to capture this picture, so that is not possible. Okay, so this is just an artist illustration of our galaxy, made based upon real data. Okay, for example, by tracking all the stars and gases in our galaxy. So what defines a galaxy? So usually you will hear people define galaxy as a group of stars, but it's actually more than that. Okay, it is a group of stars, gas and dust, planets, black holes, dark matters, and other things like comets, asteroids, neutron stars, and so on. Okay, so it's more than just a group of stars. And this is our galaxy, again, the Milky Way, and we are located right there. Okay, our solar system is located about there in one of the spiral arm of our galaxy called the Orion spiral arm. So the distance of the solar system towards the center of our galaxy is about 27,000 light years, which means that if you want to travel towards the center, to the center of our galaxy, you are traveling at a speed of light. Okay, the time it takes for you to reach the center of the galaxy will be 27,000 years. Okay, very long time. So the total diameter of our galaxy is about 100,000 light years, okay, which is about 950 with about 15 zeros at the end, kilometers. And then just to give you, demonstrate the size of our solar system as compared to our own galaxy. Okay, imagine if the size of our solar system is equivalent to the size of a 50-cent coin. Okay, as comparison, the size of our galaxy will be the size of the North America continent. Okay, so imagine 50 cents in the middle of North America continent. So it's very, very small as compared to our galaxy. And the number of stars in our galaxy is about 100 to 400 billions. So average is about 250 billion stars. Okay, just to demonstrate to you how much stars in just one galaxy, here I show you a video, a zoom in video of stars in one of our nearby galaxy called the Andromeda Galaxy. So we are zooming in at just one tiny part of the galaxy. As you can see, as we get closer and closer, the stars starting to look like sands, right? There are so many stars. All of that you can see, all the dots there are mainly stars. Okay, so there's so much stars in just one galaxy. So that is why there is a saying that there are more stars in our universe than there are sands in all of the beaches in our world. Okay, because there are so many. In 1920s, okay, we still believe that our galaxy, the Milky Way, is our whole universe. We believe that there's no other galaxies out there, and the Milky Way, our own galaxy, is our whole universe. This is in 1920s. It's not that we didn't see other galaxy. We detect or we see other galaxies out there, okay, but we didn't realize they were located outside of our solar system. We thought that the galaxy are inside of our galaxy and just part of our galaxy. Okay, so this is a picture of one of those galaxy, but at that time we called them as spiral nebula because we didn't know that it was galaxy. Okay, so this is one of a sketch from an astronomer of one of the spiral nebula. I think using his telescope, I think taken in 1845, if I'm not mistaken. Okay. So in 1920s, there is a great debate, okay, between two famous astronomers, Harlow Shapley and also Heber Curtis. Okay, Shapley said that the Milky Way is our whole universe. Okay, but Curtis argued that there are actually a lot of other galaxies out there. Okay, our galaxy is not our whole universe. So these two astronomers were debating. This is a public debate, so people can actually see these two astronomers debating with each other about their facts. But in the 1924, about 4 years later, another famous astronomer, Edwin Hubble, he managed to prove that one of the spiral nebula was located outside of our galaxy, beyond our galaxy. So that basically proved that Heber Curtis is actually right and Harlow Shapley was wrong. So our galaxy is not our whole universe. There are a lot of other galaxies out there. And so just, to demonstrate to you, this is in the 1920s. Okay, we still arguing whether we are alone or there are other galaxies out there. Okay, at this point we already have cars, we already have telephones. Okay, but we still arguing about these things. So that is just showing you astronomy is quite slow progressing. Okay, because in contrast, astronomy is actually it's the oldest natural science. Okay, but the progress is relatively slow. Okay, but we are starting to catch up now. Okay, so back to this image here of a spiral nebula here. So this was in the year 1800. So what it looks like today using more advanced telescope. So this is how it looks like, the real picture of this spiral nebula. Okay, so this is actually one of our nearby galaxy that we call as M51 or the Whirlpool Galaxy. So the spiral nebula that those astronomers looked at before is actually the M51 galaxy. So how many galaxies there are in our universe? So this is a Hubble Telescope, which I'm sure a lot of you are familiar with, the Hubble Telescope. So Hubble Telescope look at one part of the sky or one part of our universe here in the box here, the XDF box here, you can see. So it look at this part of the sky. And then as comparison, I just want to compare the size of this part of the sky with the size of the moon. Okay, so as you can see, is quite small as compared to the moon. Okay, so if we zoom in at this part of the sky here, at that box here, this is what we see. Okay, so what you are seeing here, all of these are actually galaxies. Okay, so in this picture alone, there are thousands of galaxies. So this is just coming from that one tiny part of the sky. So that means that in our whole universe, there are billions, millions of galaxies out there. So how does the Milky Way compare as compared to the other galaxies out there? Okay, again, we think that our galaxy is massive and a lot of stars and so on. Okay, but how does it compare with other galaxies out there? Okay, so this is an image of one of our nearby galaxy called M87. So if you remember, this was the one that the picture of the black hole was taken. So the black hole is in this galaxy, M87 Galaxy. So this is the picture of the galaxy. The diameter is about 1 million light years. Okay, so the diameter of our galaxy just now was 100,000 light years. So this is how our galaxy compared to this galaxy. So quite small as compared to this galaxy. What about if we compare it to the biggest galaxy that we've discovered so far, IC 1101? So the diameter of this galaxy is about 6 million light years, okay? So 6 times more than the M87 diameter. So if we compare this galaxy to the other two galaxies, including our galaxy, this is what it looks like. So you can't even see the Milky Way here. So it's very, 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 very small as compared to this galaxy. Okay, so now I would like to zoom in a little bit towards the center of our galaxy. So when astronomers look at the center of our galaxy many, many years ago, so these are all stars, the white dots are all stars, they noticed that the motion of the stars near the center of our galaxy is quite weird. Okay, so for example, if you focus on these stars here, okay, at some point, they seems to be orbiting an object, but it's invisible. Okay, and then at some point, you can see that the stars start to move very fast. Okay, very fast. Okay, so the motion is quite weird. So astronomers try to measure the mass of the invisible object that these stars are orbiting, okay, using dynamical technique, and they measured that the mass of the invisible object is about 4 million times the mass of our sun. So this directly confirm that the invisible object that the stars are orbiting is actually supermassive black hole, confirming that our galaxy has a supermassive black hole at the center. Okay, because the mass limit for a supermassive black hole just now is at least 1 million times the mass of our sun. So the mass of our black holes is 4 million times. So that is what confirms it as a supermassive black hole. Okay, so the name of our supermassive black hole, we call it as Sagittarius A star because it is located near the Sagittarius constellation. So this image here, I just want to show you an image when the black hole one of the brightest point of the black hole. Okay, in 2013. Okay, this image is in 2013, taken using X-ray telescope Chandra. So as you can see, at some point the object or the radiation starts to increase very bright. So that is actually when the black hole is eating a nearby asteroid that comes too close to it. Okay, so that is just a fun fact about our black hole. Okay, so what will happen to our galaxy at the end of the day? Okay, so this is the Milky Way, our galaxy. So this video here will show you a simulation of what will happen to our galaxy and its nearby galaxy. So this one is the Milky Way and this one is our neighboring galaxy called the Andromeda Galaxy. And they are actually moving towards each other at this point. Okay, and in about 5 billion years from now, we predict that these two galaxies will start to collide and merge with each other to form a much larger galaxy. So as you can see from this simulation here, the two galaxies has started to collide, and at some point it will completely merge together to form a larger galaxy, like you can see now. Okay, so that is what would happen to our galaxy in about 5 billion years from now. So that is about the same time when our sun will evolve into a red giant as well. Okay, so I think that's it from me. Any question is welcome. Thank you.
Thank you very much, Dr. Adlyka. Wow, the simulations and also the video sharing is very nice. So sometimes I also like to Google, but I think I did not find any similar image. I believe how did you retrieve those videos or images?
YouTube's got some videos, and then some are real data as well from the telescope database and so on.
Okay, cool. All right. So basically, I have had a couple of questions here. Some of them coming from the Facebook as well as from YouTube. There are also some which put these questions in our registration form. So let us go to the questions from Facebook. So first question by Ibnu Mat Safri. Wait ya. Okay. Saja nak tanya, walaupun boleh Google, macam mana ya dibuat kiraan berat dan lain-lain ukuran bagi matahari yang ada di dalam solar kita? How does the estimation being done?
Kita boleh masih Melayu lah.
Boleh,
Okay, kita boleh track orbit of the object. Okay, for example star kan, dia selalu akan orbit something. Even our sun is actually moving. Okay, so we can track that, and then we know that the orbital period is related to the mass of the object. Okay, so we can use like a dynamical modelling untuk kira the mass of those stars and objects.
Oh, okay. Maknanya dynamical modelling ni means daripada observation yang pertama, then buat model, daripada modelling tu buat simulation, then boleh estimate lah dia punya berat.
It's not that complicated actually. It's not really modeling. There are equations that relates between period dengan mass of stars. Just basic Newtonian punya classical physics je lah. So once kita dah dapat the orbit or the period of the star, okay, which we can observe from telescope. Okay, once we get there, we can actually just calculate the mass of the star directly. So it's not too complicated lah, relatively.
Okay. Alright, okay. Saya ke soalan yang kedua daripada Cikgu Syahril. So ada daripada YouTube ni, Syahril Muhammad. Cikgu Syahril ni daripada SBPI Kuantan. So the question is, boleh saya tahu adakah matahari mempunyai tanah seperti bumi atau ianya sekadar api yang tiada bentuk yang keras?
Okay, so matahari ni dia macam saya katalah, star ni dia adalah a ball of gas. So basically dia adalah gas semata-mata lah. Gas, okay, so hydrogen, helium, oxygen and so on. So dia memang tak ada solid surface lah. Okay, so api tu datang daripada dia punya radiation akibat daripada nuclear fusion ni lah. Tapi basically mostly matahari tu dia adalah gas, dia tak ada tanah, dia tak ada solid surface lah.
Okay, next one daripada Maisarah Bahrim. So Maisarah tanya, Doktor, may you elaborate on dark matter? What is actually what it actually is, and in what form does it exist as?
Okay, so dark matter is something that susah sikit lah. This is not theoretical. So dark matter ni something that we cannot see, just like black holes. And a lot of there are a lot of theory lah yang kita propose dark matter ni apa, sebab kita tak nampak dia kan, so kita tak tahu dia ni apa. There are a lot of things lah. Ada yang kata dia ni adalah actually black hole jugalah, made up of a lot of black holes, so they make up dark matter lah. So basically dark matter tu adalah black hole. So there are a lot of proposed theory lah apa dark matter ni, tapi I think even now we don't really have a definitive conclusion lah on apa sebenarnya dark matter ni.
Oh, okay. Emilia Adam ada continue soalan tu ni. Dia tanya, Assalamualaikum Dr. Adlyka, could black holes explain dark matter?
Yes, so as I have said lah just now, so one of the possibility of the apa sebenarnya dark matter tu adalah dicadangkan adalah black hole lah, a lot of black holes.
Okay. Okay, ni ada few questions yang kita ada ambil daripada registration form tadi. So soalan ni I think much related dengan soalan daripada first penonton tadi. Dia ada tanya dekat sini, how do you estimate the size and temperature of a star? Is it just by only observing the sky?
Okay, so we get data by observing the object or observing the sky, and then from that we can deduce all these other parameters lah. So for example, mass tadi kita boleh observe the star and then we can get period kan daripada period of the orbit from that, and then we can induce the mass of the star from that just by using simple physics. Okay, and then for example the temperature just now we can get that temperature from spectroscopy if you are familiar with that. So we can get the spectra of this the star, and then from that we can measure or determine the temperature of the star.
Okay. Okay, this one, the next question, ada lagi 3 question boleh ikut
Boleh.
The next one, why do some stars appear to twinkle?
Oh, twinkle. Okay, so this has something to do actually with kita punya atmosphere sebenarnya. It has nothing to do with the star itself. Okay, sebab kita dekat Earth ni kita ada atmosphere. So atmosphere tu dia macam dia ada ada awan kan, ada banyak molecules and whatever. So benda-benda tu it's not a smooth distribution kan, ada different density lah, different temperature and so on. So bila benda-benda ni bergerak or whatever kan, kita ada awan bergerak lah dan sebagainya. So that is actually what causing the star to twinkle. Maybe one of the reasons lah.
Okay, next one, how are galaxies named? For example, M51 just now, Milky Way, how is there any naming system? Or is it based
so a lot of stars tu, M tu for example is from Messier catalog we call it. So that is coming from bila dulu ada astronomer Messier tu lah, dia identify galaxy and then dia catalogkan those galaxy, so dapatlah nama dia kan. So kalau kita ada discovered benda-benda lain pun kan yang new, then kita boleh actually propose untuk namakan benda tu as nama kita kan, ada galaksi Adlyka dan sebagainya. Tapi it's not just kita namakan saja-sajalah, kita perlu daftar or propose dekat International Astronomical Union tu macam tu.
Okay. Okay, ni soalan ni tanya, does Milky Way spin counterclockwise or clockwise? How do we know?
Milky Way, I can't remember the exact rotation lah, tapi we can know by tracking the stars or gases in our solar system. So we can observe the pergerakan stars kan, macam kita tengok dekat black hole tu tadi kan. So kita boleh tengok dia pusing mana kan. Tapi so from that kita boleh tahulah macam dia counterclockwise ke clockwise ke. Tapi clockwise ni also dia relatif juga, sebab alam semesta kita tengoklah kita dari mana kan. So dia quite relatif lah.
Macam video yang doktor tunjuk tadi tu, the yang paling terakhir tadi tu, how long does it take to record that video yang nampak banyak star pusing yang ada satu objek
yang black hole tu? That was a long time. I can't remember, tapi decades kot, I think. And I forgot to mention that particular discovery also results in the Nobel Prize in Physics in 2020. Dan tapi punya ambil data analisis tu sebenarnya dah lama dah lah. Tapi tahun 2020 baru dapat Nobel Prize.
Doktor, tadi kan kalau black hole dia menarik semua energy kan. Kalau white hole, is it opposite of black hole?
White hole I'm not very familiar, tapi I would expect the opposite of the black hole lah instead of sama.
Okay, ada lagi 2 soalan ni, returning question daripada Cikgu Syahrir dengan Emilia Adam tadi. So betul ke orang kata kalau masuk ke black hole ni boleh kembali ke masa lain? Atau ia sekadar teori atau rekaan lah kan?
Of course lah, itu sekadar teori je kan. Kita pun tak tahu bila masuk dalam black hole what exactly happens kan, sebab tak ada benda boleh masuk kan. Even light kita nak teropong dalam tu tak possible kan. So we don't know what would happen exactly lah, but we have some theories and that is one of the theories, tapi I would say that there is not a scientifically based theory yet lah.
Okay, last question daripada Emilia Adam ni. Why did the first image of black hole come from M87 and not from the center of Milky Way.
Okay, so in order untuk kita tangkap gambar black hole ni is not easy tau. Kita kena ada teleskop yang sebenarnya very large. Okay, dan black hole tu kecil je. Okay, it's very small. So kita perlu ada very powerful teleskop. Dan one of the reason kenapa collaboration tu ataupun astronomers tu dia memilih galaksi M87 ni sebab dia adalah antara galaksi yang dekat dengan kita dan yang quite besar lah kan, dia 10 kali lebih besar daripada galaksi kita. So kita predict that the black hole also will be relatively bigger than our black hole. So itu akan memudahkan tangkap gambar dia lah kan, lagi besar lagi senang lah kita nak nampak dia kan. So that is why one of the reason lah kenapa kita pilih M87 ni. Tapi sebenarnya kita juga dah observe the black hole in the Milky Way juga, tapi data tu belum di public lagi, dia belum announce lagi. Ada nampak ke tidak tu kita tak tahulah, kita kena tunggulah. Tapi data tu dah ada.
Okay. Okay, so kita kena tunggu nanti bila dah ada registration yang macam Dr. mention tadi. So once dah temu, dia register, then baru dia make it like public. Macam tu lah kan? Betul? Okay. So alright, so I think that's all for now. Thank you very much Dr. Adlyka for your sharing and also for your time to take the questions and address the questions. And selamat berpuasa. InsyaAllah ada rezeki jumpa lagi dan selamat Hari Raya. Terima kasih.
Assalamualaikum.
Salam.